Today we will be solving the second session 2021 for the GS. Of course, the LS can benefit from that too. I hope these videos are beneficial for you. If you have any questions, you can keep it down in the comments and I will reply using a short or a long video maybe if it needs a little bit of explanation. Okay. Now here in our case, we have an ideal battery G of electromotive force E. A coil of inductance L and negligible resistance, a resistor of resistance R, two lamps X1 and X2, an oscilloscope and switch K. Now what I want you to know, it's something I didn't mention in the previous video. When you see a generator that is connected across the coil, in this case we have self-induction. Okay, but if we don't have a generator, if we have a magnet that is approaching the coil or moving away from the coil, this is electromagnetic induction. Okay, or we can see a surface that is changing. For example, we can have a U-shaped magnet, and we can put a rod on this magnet, a metallic rod on this magnet, and we can move it to the right. In this case, we're increasing the surface. This case also is called electromagnetic induction. And the last case, which is something we don't see anymore, it's changing the angle because as we know, the flux is B. The main formula is MB dot S. And by that, I mean the number of turns, the magnetic field, the surface, and cosine between the magnetic field and the surface. Okay? If any of these values changes, that means the flux is changing, increasing or decreasing. And in this case, we have electromagnetic induction. This is in the previous chapter. Self-induction is completely different. We have a generator and we have inductance. We're working on inductance and we have everything that we need to solve right now, okay? So some people ask me, they confuse a lot the electromagnetic induction and the self-induction. They're completely different. And the electromagnetic induction, you change the magnetic field or the surface or the angle. And the self-induction, you have a generator that is producing a current, and this current is making the coil create something called self-flux. Okay, so in this case, we know what we have in the given, and it's obviously mentioned in document 3. Now we have the first experiment. Consider the circuit of document 3. When we close the switch K, we observe that X2 glows instantly, whereas X1 glows with some time delay. Explain the cause of this time delay. I will tell you something. This figure here, it's seen a lot in the courses of the self-induction. Most of the teachers explain this figure, and it's mainly the most figure that is seen in self-induction because it was the experiment done at the beginning of the formation of self-induction, so it is really important. Now, what do they mean by explain the cause of this time delay? When we have the current flowing, the coil is known to have one thing. The coil always does the opposite of what should be done. Okay, so if we have a generator and the generator is increasing a current in the circuit, the coil works in the opposite way and tries to decrease this current. However, if we don't have a generator, we cut off the generator and we have the current I1 that is flowing in a specific direction, as we all know, the coil will feel that the current is decreasing over time because we cut off the generator. So it will behave as a generator itself and it will help the current to flow in the direction that it is already flowing in. Okay, so I talked about that in the previous video, and there is like an exercise talking about the establishment of the current and the decay of the current. So if you're struggling with that, the last video is really important. Now, how can we explain that? We simply have to say that we have a generator, and I will write that. We have a generator. When we close the switch, the current will increase. This increase will create a variable self-flux. Okay, because as we already know, L is equal to Li. So if I is increasing, the flux will increase and the other way around. Okay, so if the current is increasing, the flux is increasing. When the flux is increasing, that means the derivative of this flux is changing. It's not zero anymore because the flux is not a constant, it's changing, it's a variable. And we all know that every time we have a derivative of the flux, we have something called EMF or back EMF. Okay. So we will have an EMF, and if the circuit is closed, we will have a current that is working, induced current, let me say, induced current created by the coil that is trying to oppose the generator and what the generator is trying to do. Okay, so the formulas you memorize, they have a meaning. Don't just memorize things, they will tell you the whole story. So the flux is equal to Li, and since I is changing, the flux is changing, so E is equal to minus the flux over dt. And we all know that the flux is Li, so its derivative will be minus LdI over dt. And I mentioned that L is a constant, that's why we can keep it outside the derivative. Okay, the increase in the current, and I also excuse me, mentioned that in the previous video, why it's increasing, why the derivative should be positive, and all of that. So you can see the note. So what I'm trying to say here is to just write a simple sentence that proves why there is a delay. The delay is happening because the current that created by the coil is simply opposing the current of the generator. It's not letting it be by itself easily. So when we close the switch, this is question one. When we close the switch, the current, the current increases, obviously. And since we have, so the flux increases because they are related, obviously, using the formula flux equals Li. Okay. The variation of the flux uh, will help the coil create around its poles an induced EMF, which makes the coil have across or on its poles have an induced EMF. Induced EMF, and if the circuit is closed, then this EMF, which creates or permits, let me say, which permits a flow of an induced current that opposes the change or the increase of the original current. And that's really important because I think the conceptual questions uh, make the students feel like they're stuck. You're not stuck. And by the way, since we have that opposes the change of the current, so the lamp will have a delay. You can write this in your own words. You can write that in your own words. And this is, by the way, what we call according to Lenz law. The whole thing that I just explained here is what we call Lenz law. And some students feel stuck. By the way, you can memorize these steps by putting them in form of a chain. I always tell my students, when you have increase in the current, this thing will make the coil have an EMF across its poles. And this EMF, if the circuit is closed, if the circuit is closed, this will give an induced current. And this induced current will oppose the current that we talked about at the beginning. So if here we have an increase, here it should work to decrease this current. Okay, it should work in the opposite way. And this induced current causes a time delay, as simple as that. Okay. In electromagnetic induction, the chain is even bigger, but it's fine for now. We're working on self-induction, and it's mainly the most important chapter. Now we explained part one. We're done. Second experiment. Consider the circuit of document 4 given R equals 100 ohm. And we have an oscilloscope that is connected to L, the coil. No, I'm sorry. It's connected to R and L, both of them together, and to just R only. How did I know that? Some people don't know how to read the graphical study or the how the oscilloscope is connected across the components in a document. Every time you want to know what the oscilloscope is trying to measure, you see what's in between the mass and Y. So between mass and Y, the first one we have R. So the first channel is measuring simply R. And the second channel is measuring the whole thing from the mass to YB. When it's measuring the whole thing, that means it's simply measuring the battery or the generator that we have. Of course, we're not trying to put several components under one channel. We're trying to measure one thing and how it's changing over time. So you don't say the oscilloscope of channel 2 is measuring R and L at the same time. It's measuring the generator. Now, as they said in 2.1, an oscilloscope is connected as indicated in document 4 in order to display two voltages as function of time. Indicate the voltage displayed by channel YA and the displayed by channel YB. Obviously, this is what I said. So 2.1, channel 1, which is responsible for YA, is measuring the voltage of the resistor R. And channel YB, channel 2, YB, is measuring the voltage of the generator. Okay. So 2.2, determine the differential equation. I think this question is very, very repetitive. But now here it's a little bit different. Because usually they ask us about I. Why are they asking about you are here? It's a little bit different. But technically it's the same steps that we're used to. So 2.2, we simply have to say, we have the generator, it's giving out a current to the coil and R. So simply we start with the law of addition of voltages. U of the battery is equal to UL plus UR. We're so familiar with this expression. We just replace each one of them by their formula. UB, I remind you, it's E minus RI, but we don't have internal resistance, so we can get rid of RI. UL, it's the coil. It's RI minus E. And E, it's minus LDI over dt. If you feel like you need a little bit of more explanation on why is that happening, you can go back to the previous video. So Ri minus, instead of E here, we will be putting the formula of E, which is minus LDI over dt. And you will get Ri plus LDI over dt. I got my UL. And that's great. UR, simply, it's Ohm's law, Ri. So, usually this is what we do. But now they don't want I, they want UR. UR, that means keep UR as it is. So UL is replaced by RI plus LDI over dt. Plus UR, I'm not going to replace it as I'm used to by Ohm's law. No, because they want UR. I cannot change it, as simple as that. Now, and I will remind you that sometimes the internal resistance of the coil, the small r, is also zero. So be careful. Don't add just random variables that do not help you with anything. So you go back to the given and you check, what do you know about the coil? So we have a coil of inductance L and negligible resistance. So you can remove the resistance. Okay. Hmm. So here I will remove RI and I will get E equals LdI over dt. Now my problem is I have two variables. I have I and I have UR. No, I need only UR. So I have to find a way that can help me replace di over dt by UR. The only thing that I know that relates the voltage of the resistor and the current is Ohm's law. Okay, but you ask me, you will tell me, okay, but you have in the differential equation, you have di over dt. So in the formula of Ohm's law, we have I. Fine, find its derivative on both sides. You're not doing anything wrong if you derive both sides of the equality. So dur over dt equals r. It's a constant, so we can keep it out of the derivative. Di over dt. And this is my di over dt that I'm searching for in the differential equation. So simply, di over dt that I know in the differential equation should be replaced by dur over dt, and we take r to the other side, we will have 1 over r here. Okay, because di over dt was multiplied by r, so r should be divided on the other side. Okay, and that is here even more. So it will be 1 over r dur over dt. It's equal to di over dt. Okay, now the I over the T will be replaced. So we have E equals L. Instead of the I over the T, we will be putting 1 over R dur over dt, and I solved my problem because the whole differential equation is about UR. So E equals L over R dur over dt plus UR. And this is my differential equation that I'm asking for. Okay, now you have one more step that they might ask you for. Keep the derivative by itself. What does that mean? Sometimes they ask you to find a differential equation which has dur over dt by itself without a coefficient like L over R. So you divide the whole thing by L over R. Okay, so you can remove the coefficient of dur over dt, and that's completely possible. Okay, so what do we get in this case? We will get E over R L, divide by a fraction, you just simply switch it, equals dur over dt plus R over L ur. And this is my final version that they might ask for in an official exam. Now, let me start with the 2.3. The solution is blah, blah, blah. And obviously, this is known by now that every time I find a differential equation, whether it's UR or I or UC, when I used to talk about the capacitor, they all have the same solution because I'm getting to the same differential equation. And every time I tell you that you see this question and they ask for the constants A and tau, or they ask you to verify that this solution is actually a solution, all of these types of questions, they're asking you for the same thing. Just take the solution and replace it in your differential equation. Okay, so in 2.3, I will write my solution in front of me. UR equals A 1 minus E minus C over tau. I prefer to expand so I can solve mathematically correctly. Sometimes the parentheses can make you feel stuck. Now, the differential equation that I got in the previous question, it's E equals L over R. It's E equals L over R. dur over dt plus UR. Okay. Now, as I can see, I have a derivative in the differential equation and I have the solution. The solution is already got. Great. Now, my only thing that is missing is dur over dt. I have to find it before replacing anything. So we have to find the derivative of this expression. The derivative of a, which is a constant, is 0. But when a is multiplied by a variable, it doesn't disappear. So we have to keep here a and the exponential. And if you watch the previous videos, you can tell that I always say keep the terms as they are. Yani minus a, keep it minus a. Exponential, keep it exponential. Just leave a small space in between So we can write whatever next to the time on the line. Okay, whatever you have exponential of something time. This something you should put it on the line, which is the minus and over tau. Okay, because these two are next to the time, and of course we have to put one on the numerator. So we will be getting a over tau, e minus t over tau, and this is my derivative. Now I got the derivative that I was asking for in here. Now I have to replace them in the differential equation. So it will be like this, a differential equation. E equals L over R. The derivative, I will replace it in blue, which is A over tau, E minus T over tau. Plus, it's my solution. I have to also replace it by A minus A, E minus T over tau. Okay, then. So, first step, we write the solution. Second step, we find its derivative. Third step, we replace them in the differential equation. Okay, fourth step, we have to take exponential as a common factor. So I have to take e as a common factor, minus t over tau. And I open a big bracket. The terms that have exponential are the ones in red. This term here has exponential, and this term here has exponential. So I took their exponentials and I will leave only the terms next to the exponential, which is L over R times A over tau, plus, no, it's not plus, it's minus A, and I close. Now you ask me, we still have A in the middle, what do I do with it? You keep it outside, it doesn't have an exponential. Now, the last step and the most important step, that the constant on the left is equal to the constant on the right, always. So E is equal to A. I found my first constant, that's great. The second thing you have to do, you have to tell me that the exponential can never be zero. And how can I have an exponential on the right side of the equality, but I don't have an exponential on the left side? How is that possible? It's not possible, simply. So the coefficient next to the exponential should disappear. So I can make the exponential from my equation disappear. So L over R, A over tau minus A equals to 0. And we take each one of them on a side, we will get A and A on both sides. We can't simply remove them. I forgot my tau. So I will get L over R times 1 over tau equals to 1. Just simply put tau on the second side of the equality. You will get times tau on the other side. So simply L over R equals tau. So this question, it's made out of 5 steps. Write your solution. Expand it if you need. Find the derivative, replace them in the differential equation. Those are 3 steps. Once you replace them in the differential equation, the fourth step, you have to take a common factor. Then the last step, you tell me the constant on the left is equal to the constant on the right. And whatever the coefficient of the exponential is always equal to 0. Because I cannot have an exponential on the right and not on the left. It doesn't work. How can I have a variable on the right side and not on the left side? That's impossible. Okay. And as I always say, tau should be L over R always. Sometimes they try to ask you to find 1 over tau and they call it beta. Sometimes, like the previous video, sometimes they try to tell you to find, let's say, minus 1 over tau, which is D. The function, the expression that they give you sometimes might change, but the answer should always contain for tau, L, and R. It never changes, so be careful what you're writing. Okay, so if you found A and tau, and I'm 100% sure they're correct, so great. Show that the voltage across the resistor in the steady state is UR equals to E. So steady state, that means an end of the curve. And obviously I can see that the curve is coming up and it's getting steady and constant at this specific value, which is, if I project it on the y-axis, it's 10. So you are simply, it's 10, and simply it's E. But they did since they didn't tell you in the given that E is equal to 10, how can you be sure? Then this is really important. You know that you are, it's equal to E, it's equal to 10. But you cannot simply say you are is equal to 10, so simple it's equal to E, because you don't know that E is equal to 10. It's not in the given. Okay, so what are you supposed to do? You have to use your solution. Always go back to your solution if you don't know a specific number. So what do? I write my solution in front of me. It's my escape and the differential equation too. They are really important. UR equals A, 1 minus E minus T over tau. Okay? They told me at the steady state, that means the time is very big already because we already reached the steady state. So what do I say? I say that I'm trying to find UR when the time was approaching infinity. And what do I mean by infinity? Infinity doesn't mean that we have a very huge number that we don't know what it is in math, like in math. No. In physics, as long as the time is big enough to say that the experiment is done, this is what infinity is for me. So we all know that at tau we have 63%, at 5 tau we reach the max and there is nothing else to be done here. So everything above 5 tau for me is infinity. Okay, so replace the time by infinity. Of course, replace A and tau by their values. Tau it's equal to L over R and A is equal to E. So E, 1 minus E minus T over tau. So it's L over R. Okay, so you can simply just put R next to T above because you switch the complex fraction that is in the denominator. So you will be getting minus R T over L. Okay, now replace your time with infinity. You will be getting UR equals E 1 minus E minus R infinity over L. And I don't care about R and L anymore because they are multiplied by infinity. So the whole fraction here is going towards infinity. And what is the exponential? Exponential of minus infinity, because we have minus, don't forget. Minus infinity, it's simply 0. It approaches 0. The exponential of minus infinity in math approaches 0. So UR equals E1 minus 0. So UR equals simply E. And this is how I prove it. You know, you can use the graph and you tell me that UR is equal to 10 at the steady state. And if you know by the given here, if they gave you on the given that E here is also equal to 10, then you can say both of them are 10, so they are equal to each other. But since they didn't give you E, how can you be so sure that UR and E, they're both 10? So this is when you have to use your solution. Now, the last part, the curve of Dawkins 5 represents UR as a function of time. Obviously, we can see. Referring to Dawkins 5 indicate the value of E. We just said that UR equals to E at the steady state. Okay, and I can see graphically that the steady state here, when the graph was horizontal, it was 10 volts. So UR equals E equals 10 volts at the steady state. So simply E equals 10. And what is E? It is the ideal voltage of the battery. So when the battery was still new and original, it has inside of it 10 volts to function. Okay. Sometimes people forget what E is. E is the ideal voltage of the battery. And because the battery is connected to the resistor will take the voltage of the battery till after 5 tau. It will take the whole voltage. This is when the battery will become null and UR will be max. Now, 2.5.3, define the time constant tau. Tau, that's a very good question, by the way. They give me just 1 point for nothing. You have to know the definition. Tau is a time constant, and it's not any time constant. It's a special time. Every time every time, no matter what the experiment is, no matter what the voltage is, no matter what the coil is, every time at tau, which is L over R, I always have 63% of the maximum value. So what I'm trying to say, why do they call it tau? Why is it that important to name it by itself? Because every time, no matter what the maximum voltage is, no matter what the resistor is, no matter what the coil is, every time at this specific time called tau, and we will see where it is on the curve, I have 63% of the maximum value, which is 10 in my case. So it's really special. It's not just named tau for nothing. Now, 2.5.2, define it, just write a sentence about it. Tau is the time where the resistor, in our case, because the graph was given about the voltage of the resistor, where the voltage of the resistor reaches 63% of its maximum value, which is in my case is 10. Okay. Now, use document file to determine the value of tau. That's really easy and that's really important. And you saw that in grade 11. And it's the best question, honestly. Now, they ask you to find the definition. They didn't have to. You simply have to know that it's 63%. So in 2.5.3, you say that at time equals tau, at this specific time tau, U of the resistor should be 63%, or let me say 0.63 of the maximum value, which is 10. So your R at this specific time should be 6.3 volts. I go to the curve and I find where 6.3 is. It's almost like it's here. I project that on the curve and I will see that the curve is at the time t equals 1 millisecond. So using the graph, once you find the voltage, you can find tau. And if you're struggling with that, you can go back to the capacitor, even though the LS don't have it for this year. At least you can understand the basics and how important that is. So using the graph, when you are equals 6.3 volts, I project that on the curve, I will get that the time t, which is tau, 1 millisecond, which is 10 to the power minus 3 seconds. By the way, there are 3 ways to find the time constant. It's either this, and it is the most known and easy and really fun question about tau. Now we have a second method is when they draw the tangent for you. They draw the tangent for you. You don't draw it by yourself. Sometimes you can mess it up. So what about the tangent? They would give you the same graph, okay, but they will draw the tangent at t0 equals 0. The tangent to the curve at this point 0 here. And this thing will be drawn like this, okay? The point of intersection between the maximum value, which is this line here that I just drew, and the tangent, the point here is the time tau. But if they do it for you, if they don't, you don't draw it by yourself, but maybe you do it wrong. You'll get the wrong answer. Okay? So the one that we did and the tangent are graphical ways to find tau. We have one last theoretical way, which is tau equals RC, and they give you R and C so you can get tau. So 3 methods to find tau, and I'm sorry, I told you R and C. I mean R over L, or L over R. So tau equals L over R. They give you L, they give you R, then you can find tau. Excuse me, I said RC, this is in the capacitor. Okay, now I'm not talking here capacitors, I'm talking about self-induction, so it's L, not C. Okay. The last part, it use the value of L. This is what I just talked about here. So 2.5.4, They asked you about tau in 2.5, 1, 2, 3. They asked you about tau. So indirectly, they're telling you use the formula of tau, which is L over R. Okay, I know R. I know tau, it's 1 millisecond, and I know R. At the beginning, they told me that R is 400. I'm sorry, 100. 100. So I simply replace that. Tau is 10 power minus 3, and sometimes people forget to convert to SI. That's a really big mistake. You're getting a wrong answer. And if you get a wrong answer and you solve the whole thing wrong, some teachers might not consider it because they already have their answers in front of them. So 10 to the power minus 3 equals L that I'm searching for over 100. Simply I cross multiply, I will get 10 to the power minus 3 times 100 will be 0.1 Henry. And I got L. There's a lot of things to explain in this chapter, but as a concept of solving, it's really easy to solve. But the concept of explaining things and understanding what's really happening, this is what takes time. So this is why I'm uploading this video or the videos of the self-induction in general, because there are some ideas that are really hard to grasp, that you have to understand. Okay. So thank you so much, guys, for watching. Subscribe, like, support. Everything is really appreciated. Comment below. I can reply to all the comments. If someone is struggling with a specific idea in the chapter, this business is not only me explaining physics or math. We have a center, and we have private tutoring lessons one-on-one. And I'm trying to upgrade this business uh, to upload books that feel similar to the official exams and feel similar to grade 10 and 11 and everything they get asked in their exams. I'm still working on that, and your support means a lot. So subscribe, share, and everything if you find that beneficial. And thank you for watching again.